Greetings from the Hermitage, and welcome to this review of factoring and the greatest common factor. We've made it this far in this semester so far, and we've gotten to the point where we're working with equations that involve multiplication and addition or subtraction. And we know so far that whenever we have an equation like this, that the first thing we want to do, the easiest thing that we can do, is zero out the constant term. That would look like this. This is 3x, subtract 7/16 to zero that out. We use the additive inverse, and the additive inverse states to add the opposite. So we would add positive 7/16, and to keep the equality in the equation, we would add exactly the same thing to the other side. The additive inverse says that's a 0, so now we have 3x equals 5 divided by 24, add 7 divided by 16. This becomes the most difficult part of solving this equation for this value of x. And to be able to do this, we need to get common denominators on both of those. And so we're going to review some of the things that we have to know before we can go about getting the common denominators. And those things that we're going to review is factoring and the greatest common multiple. So why learn factoring at all? Well, one, it's useful in reducing fractions. Two, it's useful in adding and subtracting fractions where a common denominator is required. And three, ultimately, it's a major topic in high school and college algebra, and you'll be working with rational expressions. Rational expressions have both letters and numbers in them. Gets a little bit more complicated when you have that, but if you learn these basic techniques with just numbers that we're covering today, your life will be a lot easier once you get there. Now, there are some useful things that we should know as we go about factoring. First of those is that factoring means to write a number as a multiplication. So we can take most numbers and rewrite it as the product of two or three other numbers. Now, a prime number is one that only has 1 and itself as factors. In this case, I showed you 7. A couple other examples are 3. 1 times 3. 5 is an example. 11 is an example. These will typically be odd numbers. The third thing that we should remember is that a number with either a 0 or a 5 in the ones place has 5 as a factor. So if we had a number like 25, we have a 5 in the ones place. You could factor 25, factor out 5 from that. Fourth thing, a number that is even has 2 as a factor. Something like 6. You can factor out a 2. You can write 6 as 2 times 3. You can write 12 as 2 times 6. And finally, a number whose digits sum to a number that has 3 as a factor also has 3 as a factor. We'll take 72 as an example. We add the 2 digits, that's 7 and 2. That adds up to 9. You know that you can write 9 as 3 times 3. So since you can factor 9 as 3 times 3, then 72 also has a factor of 3. And so we could write 72 as 3 times 24. So let's go ahead and move into actually factoring some numbers. We're going to reduce this fraction, 16 over 24. Both 16 and 24 are even numbers, so we know that 2 is a factor. And I'm going to demonstrate using the factor tree. So I'm going to write 16. And I know that 2 is a factor. If I divide 16 by 2, I get 8. 8 is an even number, so I know that I can factor out a 2, and that would leave me a 4. 8 divided by 2 gives me 4. 4 is an even number. I can factor out 2, so 4 divided by 2 gives me 2. And I'm finished at that point because 2 is a prime number. It can't be factored any further. So these are all of my factors. So I'm going to write 16 as 2 times 2 times 2 times 2. And now I'm going to do a factor tree for 24. I know that 24 is an even number because 4 is an even number. So I'll factor out 2. 24 divided by 2 gives me 12. 12 is also an even number. I'll factor out 2. 12 divided by 2 gives me 6. 6 is an even number. I can divide out the 2. 6 divided by 2 is 3. 3 is a prime number. It cannot be factored any further. So these are all my factors. I'll write those here. 2 times 2 times 2 times 3. We're almost finished. We want to look for numbers in the numerator that are also replicated in the denominator. And so we have 2 here, 2 and 2. This whole thing becomes my greatest common factor. I can write that. 2 times 2 times 2 is 8. So that's going to be 8 times 2 over 8 times 3. 8 divided by 8 is just 1. So when I reduce 16 over 24, once I factor out the greatest common factor, I'm left with the reduced fraction, which is 2/3. Box in the answer. Let's now reduce a fraction when 5 is a factor in both the numerator and the denominator. I'll use the factor tree once again. From our rules in factoring, we know that any number that has a 0 in its ones place can be factored by 5. So we'll start with 50. Our first factor is 5. 50 divided by 5 gives me my other factor. That'll be 10. 10 has a 0 in the ones place. So we can factor out another 5. 10 divided by 5 gives me 2. 5 is a prime number, 5 is a prime number, and 2 is a prime number. So those are all my factors for 50. So I'll rewrite this as 5 times 5 times 2. 5 times 5 is 25, times 2 is 50. We'll do the same thing for 75. The factor tree for 75. We'll factor out a 5. 75 divided by 5 is 15. 15 has a 5 in the ones place. That means we can factor out another 5. We'll write that here. And then 15 divided by 5 is 3. All of these factors are prime numbers now. They can only be factored by itself and 1. So I'll write those factors in the denominator for 75. Once again, we're looking for numbers that are both in the numerator and the denominator. These are the ones. These common factors become the greatest common factors. And we know that 5 times 5 is 25. Same thing in the denominator. And we're left with 2/3 here. 25 divided by 25 is 1. So 50, whenever you reduce it to its lowest terms, is going to be 2/3 because these 25s divide into 1. Box in the answer. Finally, let's reduce a fraction where 3 is a factor. Now, I know that 3 is a factor because if I add 2 plus 1, that equals 3, and 3 is a factor of itself. Same thing with 27. 7 plus 2 equals 9, and we can factor 9 into 3 times 3. So both of these numbers, the denominator and the numerator, can both be factored by 3. I'll do the factor tree now for 21. We know that 3 is a factor. 21 divided by 3 is 7. 7 cannot be factored any further. It's a prime number. So I'll go ahead and write the factors like this. 3 times 7. Now let's do the factor tree for 27. 27, you can factor a 3 out of that. 27 divided by 3 is 9. 9 can be factored by 3. 9 divided by 3 is 3. All of these numbers are prime factors. They cannot be factored any further, so I'll write those down. 3 times 3 times 3. In this case, there's only one 3 up and down. That will be our greatest common factor. So this will become 3 over 3 times 7 over, and 3 times 3 here is 9. These 3's divide out, becomes a 1. 1 times 7/9 is 7/9. So 21 over 27 is our answer. 21 over 27 reduces to 7 over 9. Let's do a quick summary. In this video, we discussed using prime factors to factor numbers, and we use those prime factors to determine the greatest common factor in a fraction, and getting the greatest common factor allows us to reduce fractions. And in a future video, we'll see how we use the same technique to get a common denominator for two fractions. It's a quick, short video, and at the end of the day, there's only one thing left to say, and that is that's all, folks. FOLKS. Thanks for viewing. Thanks for learning. Be safe. Con cuidado.